Okay, calculus remotees. Looking like we are going to be giving this an honest effort to have school via Google Meet, YouTube videos, and assignments sent to me through pictures and emails. So, our job is to make the best of this situation as we can, and I'm certainly willing and able to do that. And it's actually been a fair amount of fun creating these videos. I've already made the Algebra 1 and Algebra 2 class videos, so here I am going into my fifth one. But yeah, it's relaxing, and I hope it's relaxing for you too, just to sort of sit and watch and learn. You have a lot of tools at your disposal. One tool is the pause button. So you can pause and reflect and think about what I'm talking about. You can rewind. You can watch it multiple times. Okay, so it'll just be a YouTube link. The general scenario is this, that math classes meet on Tuesdays and Thursday mornings. And by meet, I mean that I will have posted the link to my video by that time. And come Tuesday and Thursday mornings, as you wake up, watch the video. And then after the video, you should be prepared to do the assignment, which will also be posted at ThinkWave. So a couple of additional things. I will be in Google Meet from 9:30 to 10:30 and from 2:30 to 3:30 to take questions from my students on Tuesdays and Thursdays. I think I'll be in there a few other times. Whenever it says tutorial on the schedule that was put out, I'll be there. So you can use those times. It'll likely be a little chaotic because all my students will be there, not just calculus students. You can certainly email me, and we will work our best to, go back and forth that way. Okay, so let's see. The long and short of it is that I have a job to do, and that is to prepare these lessons and ask you to do some work. And you have a job to do, and that is to watch the lessons, do the work, and send me your assignments by 8 p.m. the same day that you watch the video. Since we only meet twice a week, it is imperative that you do that. Now, in order to get credit for the assignment and thus keep your grade up, and in order to get attendance for that day, you definitely need to email me your assignment by 8 p.m. So please work hard to make sure that that happens. Okay, so I'm going to jump right in to what we're doing. And what we're going to do today is we're going to continue on in Chapter 7. And we have been busy integrating by various means, most recently preparing integrands in fraction form for table entries. This is a process known as partial fractions. Okay, so the next thing we're going to do is tackle some improper integrals. And you'll need to know what it means to be an improper integral. And there's two different definitions as to what an improper integral is. One of those is when the limits of integration are infinity or negative infinity. Okay, so that makes what is known as an improper integral. And I'm just going to start with what one looks like. So this is an integral of 1 over x squared dx. And that integral is going to run from 1 to infinity. Thus, it is an improper integral. And it can be quite complicated to take such an integral using the fundamental theorem of calculus when you have infinity or negative infinity as one of the limits or both of the limits of integration. Okay, so let's proceed. And in so proceeding, I'll develop a strategy, and then we'll take some notes on sort of like the fundamentals and the language that go with this. And that'll be a little abstract. And then we'll get into some more concrete examples. And some 30 minutes down the road, I'll get into the second type of improper integral. Okay, so the way that I'm going to take this integral is a little sneaky, and the way I'm going to do it is I'm going to rewrite it as the integral of, I suppose I can go ahead and call it x to the negative 2. I'm going to need that at some point. X to the negative 2 dx from 1 to arbitrary variable b. And then we're going to think about running the limit as this upper limit goes to infinity. So that's the same conceptual idea, but it will allow me to sort of show the mathematical moves more easily. Okay, so then if I can just attach the limit as b goes to infinity, and then go ahead and take this integral. So I'm going to take the integral, and that would be x to the negative 1 divided by negative 1. So then I throw a negative sign out there, and I guess that's the end of that. And then I'm going to evaluate that from 1 to b. A lot of times we draw the bar, but when I use brackets, I just sort of let the bracket do it for me. And okay, so now I've got the limit as b goes to infinity. Now my brackets might come in more handy. Let's see, what am I going to do? I'm going to do this negative 1 over x, right? That's what this is. I'll squeeze it in here so I'm not skipping too many steps. And then we put in the upper limit b, and then we subtract from that whatever happens when we put in the lower limit. And so the lower limit is 1, it'll be negative 1 over 1. Okay, so that's using the fundamental theorem, and I get the limit as b approaches infinity of negative 1 over b plus 1. Which by the rules of limits, you can run the limit on this one and you can run the limit on that one, but I'll just run it simultaneously. And I think that we can all see that that's going to go to 1. Because this part, I'll do it in a second color, this part is going to go down to 0 as the bottom gets bigger and bigger and bigger and bigger. Okay, so that is just a starter improper integral. Now, let's think about this for a second. What does an integral do? It calculates the area underneath the curve from lower limit to upper limit. Well, what does 1 over x squared look like on the interval 1 to infinity? All right, well, I'll give you a little visual on this one. So 1 over x squared looks like, well, let's put in some numbers. 1, 1, 2 1/4, 3 1/9, put in a half, you're up, well, let's see, up at 4, right? If you put in a half, then that's 1/4. So at half, you're up at 4, say. Okay, and you get this sort of looking thing. And then I'm not interested in what's going on over here in the negatives, but when you put in the negatives as a result of squaring, anyway, that's what the function 1 over x squared generally looks like. Okay, now let me just do sort of a zoom of that so we can start thinking about area underneath it from 1 to infinity. Whoa, 1 to infinity. Okay, so it would look something like this. And the x-axis is acting like an asymptote. This function never gets down there. And we're going to go from 1 trying to make it look like 1, 1 is here. We're going to go from 1 to infinity. So we're talking about an integral that captures an infinite amount of space. This area under here goes on forever. And this is one of the coolest, craziest things. Even though it occupies an infinite amount of space, in theory, the amount of area contained within that space is a finite number, 1. Crazy. So this has always sort of been a cool thing. A big cautionary tale, though. Not every scenario like this actually converges to a number. And sometimes these infinite spaces have infinite area, and sometimes these infinite spaces, in quotes, have a finite value. And then we get into the language of divergent and convergent. If it being the area, if the area is infinite, then it diverges. And then if the area turns out to be finite, it converges to a number. Okay, then. So next I'm going to go ahead and give you the book's definition of convergent and divergence. And it's a bit abstract, and then we'll reel it back in and roll into some concrete examples. Okay, so here is the calculus definition of these vocabulary words. And I'll try to point to some things and break it down for us. But, I think it's one of these things that ultimately you can go back and look up if you're starting to deep dive into the proofs associated with improper integrals. Okay, so the situation here is that we have a function f of x, which is positive. Okay, so that's above the x-axis for all values to the right of our lower limit. So we had that going on with my first example. And I don't totally like the way these are positioned because we generally start with this structure and rewrite it as the limit structure, but I'll roll with what the book has here. So if the limit as b approaches 0 of some integral of f of x dx from a to b, so then this is the upper limit, is going to infinity. If this limit on this integral is a finite number, then we say that the improper integral version of it converges. And define the improper integral to be said limit. Now, what I just did in the problem is I took the integral, used the fundamental theorem of calculus from a to b, and then ran the limit as b approached infinity. So this is a computational situation. Otherwise, we say that the improper integral diverges, otherwise being that it doesn't produce a finite number. And there's a similar definition for the improper integral that runs from negative infinity to b. I suppose here our limit would be structured a little differently, right? This would be the limit as a approaches negative infinity. All right, so that's the fundamental definition of convergence and divergence. And what I'm going to do next is just roll into the next sample problem. Okay, so let's ask the question, does a particular integral converge or diverge? So does the improper integral given by 1 over root x dx from 1 to infinity converge or diverge? Does it approach a finite number or not? Okay, so off to the races we go. we're going to redefine this thing as the limit as b goes to infinity on the integral of x to the negative 1/2 dx from 1 to b. And this, of course, is the limit as b goes to infinity on some function. And that function, by the reverse power rule, is x to the half divided by a half. And we're going to evaluate that from 1 to b. So this is the limit as b goes to infinity on 2b to the half. That's putting in b minus putting in 1. I get 2 times 1 to the half. Okay, so let's see. That'll be the limit as b goes to infinity on 2 root b minus, breaking it into the two limits this time for no reason, just to be different than I did last time. That is 2. Well, this is clearly finite. But as b gets bigger, the root gets bigger, and the root of something big is really big, so that then goes to infinity, and infinity minus 2 is still infinity, and so this one does not converge to a number. It diverges. So, does the improper integral blah blah converge or diverge? And the answer is it diverges. Okay, well, you may be interested in, well, what is the difference in the graphs? And the answer is not a hell of a lot. They look like, I mean, they go through different points, but they generally have the same shape. So you got to do the investigation. Okay, so there you go. Okay, so just a reminder, this is a video. You can pause it. You can go back. You can watch it again. So if any of these ideas don't take root, you can readjust. All right, I'm going to do one more example before I sort of come back to these two examples that I've just done, one being convergent and one being divergent, and do a little deeper dive into when is a function of the nature 1 divided by x to the power convergent or divergent. So one more practice problem, and then a little bit of a more difficult scenario because it's more abstract and asks a slightly different question. All right, then. So then this next one is for us to go ahead and calculate an integral. And the integral is going to be an improper integral. And the integral is going to be e to the negative 5x dx. So I'll bet you got the hang of this. And if you want to pause it and try it on your own and then come back, that seems like a good idea to me. Okay, so let's see. What is the integral of e to the negative 5x? I could do a u sub, but I think we know that when it's linear up here, when the interior function is linear, we get to take, the e to the u's derivative, which is e to the u, and then divide it by the derivative of that. And so I guess that's to divide by negative 5. That is to say multiply by negative 1/5. Okay, and then we're going to evaluate that from 0 to b. Okay, now I'm just going to glance. I'm wondering how the book pursues this. Because I'm thinking that, we could we can take out this negative 1/5. For by the fundamental theorem of calculus, they each have it, and then by the property of limits, you can take out a negative 1/5. I don't know that really makes our work any easier, but I'm just going to go ahead and do it. It is different than the book has done it. So if you're paralleling this with your book, here's a second option. That would be then negative 1/5, the limit as b approaches infinity. And I can evaluate this thing without the negative 1/5. So I get e to the negative 5b. That's putting in b minus e to the negative 5 times 0. My 5s aren't looking too good. Okay, so then let's see where this takes us. That's negative 1/5. And let's see, e to the 0 is of course 1. And as b, let's not skip that step. Let's just go ahead and do the limit as b goes to infinity, and this is 1 over e to the 5b, and then that's minus 1 because we've determined that. Okay, well now it's a little easier to see what happens as b goes to infinity, 5b goes to infinity, as e to the infinity, well that whole thing goes to infinity, so then this rather nicely collapses down to 0. And I get negative 1/5 times negative 1, or 1/5. So I've calculated that improper integral. Okay, so I'm going to need some room for this next one, so I'm going to go ahead and go on to the next page. The question here is different, so I think what I'll do is I'll just zap it over to that page, so I don't have to write it all. So here comes the question. Determine for which values of the exponent p the improper integral diverges. Now, I would point out that when p was 2, that was my first example, and it converged. And then when p was a half, that was my second one, it diverged. So, we're asking sort of like for, it's the next level of question, but we're asking to find like for what values of p it diverges. Find every single value of p for which it diverges, and then maybe we, have some insight into when they do and when they don't converge or diverge if they're in this format where it's the ratio 1 divided by power function. Okay. So then this, again, is a little bit complicated. And we're going to start by considering p-values that are not equal to 1. Because I'll come back to this, but when p is 1, then we don't get to use a reverse power rule. We have to do the integral using the natural log. So in all other cases, we use the reverse power rule. So I'm going to wait on the p equals 1 scenario. Okay, so then what we can do is we can consider this integral from 1 to b instead. And it is x to the negative p dx. And then by the reverse power rule, that is x to the negative p plus 1 divided by negative p plus 1. And I'll write it like this. All right, well then that's going to be evaluated from 1 to b. And when I put in the b values for x, mind you, I know there's sort of multiple variables running around with p's and x's, but my variable is x. I get 1 over negative p plus 1, b to the negative p plus 1, minus 1 over negative p plus 1 times 1 to the negative p plus 1. And then that simplifies up a little bit. Because 1 to the anything is still just 1. Okay, so now this is a bit of a thought experiment. Keep it in mind that b is going to be going to infinity. And if b's power, so let me just consider the power. If b's power is negative, then that means that this base will be down below, and as it gets big, it'll become bottom heavy and run to 0. And if this runs to 0, then this other piece becomes the value of the integral, and that is an actual number. So then that would be the converges scenario. So then the integral converges, and I'll go so far as to say that it converges to negative 1 over negative p plus 1. However, if negative p plus 1 is greater than 0, so then our base is being raised to a positive number, then the b stays up above, and this piece becomes infinity, and this piece doesn't matter. So then we would have to argue then the integral diverges. Okay, so then p-values. So this would be by subtracting 1 from each side and multiplying everything by negative 1. This convergence scenario happens when p is greater than 1, and then this divergent scenario happens when p is less than 1. So what we've got so far in terms of answering the question is determine for which values of the exponent p the improper integral diverges. It diverges when p is less than 1. Okay, but we do need to consider this case when p equals 0. So let's roll it again. When p equals 1, I think I said 0. So let's roll it again. So now we've got x to the negative 1, which is the natural log of x, which is then the natural log of b minus the natural log of 1. All right, well, the natural log of b minus the natural log of 1 is the question. E to what power makes 1? That's 0. So this then becomes the natural log of b. All right, but if we think about b running to infinity, then we're asking ourselves e to what power makes infinity, and that would be infinity. And okay, so it looks like we have another scenario where it diverges if p is equal to 1. So then to answer this question, we could say that the integral diverges when p is less than or equal to 1. And we could also write when p is greater than 1, it converges to -1 over negative p plus 1. Okay, so now I'm going to move on to the second type of improper integral. And that is a type described as follows. So we have an improper integral. And it's not because one of the limits or both of the limits of integration are infinity, but it's different. This is when the integrand becomes infinite. So we'll have to get a function out and a visual on what's going on. So let me first go to the visual and draw the function that we had a little bit ago, not in great detail, but this is the function 1 over root x. So then that's my function. And what I'm going to be interested in looking at is the fact that this has two asymptotes. On the one hand, this one is going to smush down towards the x-axis, and on the other hand, this one is going to get closer and closer to the y-axis. So it has a horizontal asymptote, but in the case of this type of improper integral, what we're interested in is in the fact that it also has a vertical asymptote at 0. So that if we attempt to find the area from 0 to something, I'm just going to choose 1, then we're going to run into the same type of dilemma. Namely, we have, and let's see, this would be over here at 1, namely that we have an infinite amount of space because of this asymptote idea, but it might actually contain a finite amount of area. Okay, so you'll notice that there's no infinities anywhere. But the problem is that this integrand goes to infinity at 0. Or said differently, the denominator becomes 0, which is indicative of a vertical asymptote, because you can put in values near to 0 but not at 0 itself. Okay, so then let's work on rolling this one out. And it's going to work a lot the same, but we're going to have to be talking about our old friends, the left-hand sided limit and the right-hand sided limit, and that sort of thing is going to come into play. In this problem, we're going to be interested in the limit as our value approaches 0 from the right-hand side. So we're going to be interested in the limit of a plus. Okay, so the way we're going to tackle this one is, again, a lot similar. We're going to be looking at the limit of not 0 to 1, but arbitrary value a to 1. I could use b there, but I'll use a. And I suppose this is still x to the -1/2 dx. And in this case, a is going to be approaching 0, the lower limit, from the right-hand side. Okay, so we've done this, and we know that this is -2 x to the half, evaluated from a to 1. I forgot to squeeze in the limit. Let me see if it'll let me do that for the most part. Okay, so let's see. Let's make this look nice. This is the limit as a approaches 0 from the right of this whole thing. All right, saved it. And let me carry it down here. That would then be the limit as a approaches 0 from the right. And putting in the upper limit of 1, I get -2 minus, when I put this one in there, I get -2 root a. Okay, so then what happens as a approaches 0 from the right? Well, one thing is that this is a positive number, but it's going to be closer and closer to 0, and this piece goes away. That piece goes to 0. And then the limit of a constant is the constant. And why do I have a negative sign issue? So let's see. Somebody save me on a negative sign issue. Well, that was a rookie mistake. Sorry about that. But there is no negative sign here. Just doing this integral, add 1 and divide by 1/2. There should have never been a negative there. So that changes this to a positive and this back to being negative. And then the answer is +2, which makes more sense because the area is above the x-axis. So again, this bizarre scenario where you have an infinite amount of space on account of that just goes up and up and up and up, but yet it has a finite area. Okay, so let's look at another one. And this one is going to be the integral of 1 over x minus 2 quantity squared dx from 0 to 2. And first, we need to diagnose maybe what the function looks like, and therefore we can decide where its vertical asymptote is and where the problem might lie. So as discussed earlier, the graph of the parent function to this, the simplest possible version of this, would be 1 over x squared. And 1 over x squared looks like this one. We had this one earlier. So it's got this half, and it's got that half. They're symmetrical. But then when you minus 2, that's the old mess with the x, and it will move it left or right. So it's going to take this function and move it over to the right 2. So maybe I'll put some markers on here so we can see better. That's 1, that's 2. And the current asymptote here is the y-axis. Well, yeah, if we move it over 2, then the new asymptote is going to be this line. Fail. So let's save me with some technology. I could have gone to this right away. I knew I had a dashed line. Okay, so then there you go. So then the problem is the upper limit. When we put in the upper limit, we cause divide by 0. That's the hint. This isn't the problem at all, but it's the upper limit that causes this piece to be improper. It causes it to be undefined, or you could think about it, how it collapses down to 0. Okay, so then the rewrite of this one is going to be the limit of the integral from 0 to b again, and b is going to be approaching 2. Let's see, we're looking at from 0 to 2, so we're interested in this area. So that means we're approaching 2 from the left-hand side. All right. So let's see, and we got our usual 1 over x minus 2 squared dx. Rewriting the limit and integrating. Now it seems like it's been a little while since we did a u sub, so let's just roll out this u sub idea real quick. Let u equal x minus 2. That makes du dx equal to 1, and du is dx. So when we write this, we're going to go, I'm going to replace these later. I'm going to back substitute, so I'm just going to let these integrals survive. It's going to be 1 over u squared du, which is the limit as b approaches 2 from the left on, let's see, that's u to the negative 2, so that's negative u to the negative 1, evaluated from 0 to b. And finally, let's put this back into position using substitution, the back substitution. It's x minus 2 to the negative 1. That's evaluated from b to 0. Fundamental theorem of calculus. I'm just going to let this be, but no, I'll fix it. Somehow should be with the bracket there. Same thing up here, frankly, but that's okay. All right, so the limit as b approaches 2 from the left, and okay, wow, we got a lot going on here. I've got a negative, and it's a b minus 2 to the negative 1. That is my variable. Minus. This one now is slotted in, so that turns into plus 0 minus 2 to the negative 1. All right, so then we've got the limit as b approaches 2 from the left on this structure, which is negative 1 over b minus 2, plus this structure, which is negative 2 to the negative 1, so that's negative 1/2. Right, let's think about this. B from the left, so sometimes I just like to think about numbers like 1.99. If you put 1.99 here, you get negative 0.01. Well, that's positive, but you have a small thing going into 1, and anyway, this thing is becoming infinity, and infinity minus 1/2 is still infinity, and we have a divergent case. So I cannot find the value of that area, for it is infinite. Okay, so I have 2 more samples left, and then you'll be ready for my assignment. And this first one just looks so easy, but it really does just point out the cautionary tale associated with running integrals and using the fundamental theorem of calculus. Okay, so like I said, this one just looks all innocent. And we're going to run this from negative 1 to 2. So, you know, without today's lesson, or maybe even with today's lesson, it would be, you know, an oversight, however, as you're about to find out. But, you know, one would pursue this problem by integrating x to the negative 4 and get x to the negative 3 divided by negative 3 and evaluate that from 2 to negative 1 using the fundamental theorem of calculus. So I suppose we could pluck out the 1/3 and drop in 2 to get an 1/8, and then subtract from that, dropping in negative 1, so that would be 1 over negative 1 cubed, still negative 1. Okay, so what that's plus 1, and then that's negative 1/3 times 9/8, because that's 8/8, so that'd be 9/8. And I suppose negative 3/8 would be, an answer. But that's wrong. And, one thing that you can do is you can always try to get a visual on what these curves look like. And while we haven't really talked about x to the fourth, 1 over x to the fourth, you realize that no matter what you put in, you're going to get a positive answer because it's to the fourth power. And when you put in 1, you get out 1. And when you put in 2, you get out 1 over 2 to the fourth, which is 16, and it's small. And so it's just another one of these, but it's more radical in terms of how it drops and turns and shrinks down. Okay, so that's essentially 1 over x to the fourth. And even though we're going from, say, negative 1 out to 2, and you can look at this and say, dude, that is not negative. This amount of area is either infinite or finite and positive, but it's definitely not negative. So this just didn't work. Okay, so why didn't it work? And it didn't work not because it's an improper integral in the sense that either of these limits is integration, or that either of these limits, when put in, causes divide by 0 or causes it to be improper or to collapse. But in between these two limits is a vertical asymptote. So therein lies the rub. So what we need to do is to break this into two integrals using a property of integrals that says we can use this intermediate value anywhere. I don't necessarily have to use 0 when you break an integral up, but in order to do this particular problem, since that's where the vertical asymptote is, it's going to be super convenient to use 0. All right, so in this particular scenario, I do have to use 0 because that is the place of interest. So now what I have is a more obvious, this is an improper integral. This is an improper integral, and I'm going to compute both of them and then find the area if it is in fact finite, or I'll decide that it is convergent. No, said that backwards. It's divergent. Okay, so then this first one. And I guess I'm just going to go ahead and refer to this one as the red one, because it looks like things might get a little epic here. I'm going to run the limit on the integral from -1 to b. That's the problem. So now b is running to 0. But let's see, I'm going from -1 to 0. I'm over here on the graph. -1 to 0. And so that means I'm approaching 0 from the left. And then that's the integral, x to the -4th dx. Okay, so then what happens with this? This is the limit as we approach 0 from the left on x to the -3 times -1/3. And that's evaluated from b to -1. And this limit is there again. And what do we get here? We get -1 over 3. Could have taken the -1/3 all the way out, but I'm letting it somehow stay in there. That'd be 3x cubed. Oh, right, but not x, b, because I'm going to go ahead and use the fundamental theorem and put in that upper limit. Okay, then I subtract from that. Now I'm putting in this one. We already got a -1/3, so now that's a plus. Here's my 1/3, and it's -1. That's going to be cubed. Okay, so this value is equal to -1/3. So I suppose I'll just write that as -1/3 down here. And this value, let's see, this b value is getting closer and closer to 0 from the left. So it's like -0.000000 cubed. So now it's -0.000000, lots of zeros. times 3, that doesn't matter, but it's a super small thing that happens to be negative that fits into, oh, infinity again. This diverges. The red one diverges. Doesn't matter what the black one does. The whole thing diverges. Done. Doesn't matter. This could be a concrete number. This is going to overwrite it. This could be another divergent scenario. Then fine. They combine to make a divergent scenario. So when one of them's divergent, the whole thing is divergent, and I can help expedite the problem. And now for the last sample that you'll need for my assignment, minus perhaps 2 challenge problems. Okay, and let's see. This is the 5th hour-long video that I've made today, and quite frankly, I am exhausted, although I am having fun. Now, because I'm so exhausted, I'm totally cheating. Bam, it's done for us. I'll walk you through it and not go through as many of the steps because I think you see what's going on at this point. So here again, we have an improper integral that's in disguise. You would have to get a visual on what x to the 2/3 looks like. And again, that's one of these cone-like formulas, which the parent function has a vertical asymptote at 0, but because we've done x minus 4, the whole thing has been shifted over 4, and the new vertical asymptote is at 4. It's the problem. And maybe more importantly than 4 being the problem, our integral goes through 4. We're running from 0 to 6. So we're going to break this into 2 integrals. We're going to go from 0 to 4, and we're going to go from 4 to 6. Now, you can use a u-sub, or you can go ahead and use the sort of cheater method. It only works when this is linear, but we can quite easily take the integral. Keep it in mind that we've replaced the upper limit by b, and b is running towards 4 from the left-hand side. We're going from 0 to 4, so we're approaching 4 from that left-hand side. Notice down here, from 4 to 6, we're approaching 4 from the right, and that affects the sign of things that happen later on. Okay, so next it's the fundamental theorem of calculus, and it's a dropping in of the b and of the -4, and in this case, this value becomes super small. It doesn't matter that it is, in fact, let's see, it's going to be negative because we're going to be putting numbers like 3.9, but it doesn't matter that it's negative. It is just crushing towards 0. Meanwhile, on this side, you have a double negative and you have an outcome. So as for this left-hand space, it has finite area, whatever that number is. Go to a calculator. Similar argument, the same integrals happen. Be a little careful. Now you're putting in the 6 first. 6 minus 4. Maybe I should point over here instead, but now that becomes 2. And this is the one that you're running the limit. And you're putting in something slightly bigger than 4, so like 4.01, but that doesn't really matter. This is going to 0, and this whole piece is going to 0, and the space over here on the right is also finite, and in fact given by that number. And so we can then compute those on the calculator and find out, whew, crazy scenario, but finite area captured by the function. Okay, so, just reiterating, these are going to be kind of big, heavy math days. That was, pretty much an hour of me doing samples, and now it's your job to go and do some problems, snap them, email them by 8 o'clock tonight so that I can look at everything and come up with a suitable plan for Thursday. Okay, I'll be in chat rooms. You'll be able to email me, and hope everybody's doing well. I'll talk to you soon.